So we've looked at transformations of other graphs in the past. So we just have to remember those transformation rules. We're going to talk about horizontal shifts, vertical stretches and or compressions, horizontal stretches and or compressions. The thing is that when we're talking about trig graphs, since they are periodic and they're wave-like, some of the vocab just changes a little bit. When we talk about a vertical shift or a vertical stretch or compression, we're going to talk about that being the amplitude of the wave. When we talk about a horizontal stretch or compression, we're going to talk about that being a change in the period for the function. Vertical shift, we're just going to call a vertical shift. Horizontal shift, we're going to refer to as a phase shift. So it's just different vocab, but it means the exact same thing as we are used to seeing. So we see this, y equals the sine of x plus 45 degrees. What we are going to do is use our calculator to determine exactly what change has occurred. But the thing to take into account is your calculator needs to be told if you are working in degrees or if you are working in radians. Sometimes the way the function is given to you is vague and you can pick yourself whether it should be degrees or radians. This is not one of those times. You look right here, we have plus 45 degrees. So this function needs to be put into the calculator and your calculator needs to be told you're in degree mode. You do that by pushing the mode button, which is in the top left section of the calculator. Push mode. There's a line that has the word degree and the word radian on it. Make sure the word degree is highlighted. If, obviously, you're given a function that has a radian measure, you would want to go into mode and make sure to switch your calculator to radian. When you've made sure you're in degree mode and you've typed it in, you want to make sure to push zoom 7. Zoom 7 is the way you can tell the calculator I'm graphing a trig function, so adjust my window accordingly for me. And that way you don't have to mess with changing the window yourself. So when we plot this in the calculator, you can see that when you do x plus 45, that is a horizontal shift to the left 45 degrees, which we've done these transformation rules before. And I stressed to you before that it's important to really practice them and experience them, not so that you have them memorized for the rest of your life, but so that on a day like this where they come up again, it is going to be far easier for you to mold this into what you're thinking if you had done all that work before. So when you add the 45 degrees in here, that is a horizontal shift because it's being added to the x, and the x-axis is horizontal. And we just have to remember that with horizontal shifts, if it's addition, that means move it to the left. So if I make my scale here 90, 180, 270, 360, the sine function would start usually at the origin. But I shift to the left 45 degrees right here. And then every single point that I would have on my sine graph, I am just going to be shifting 45 degrees to the left. Right there. And you just keep going like this. So there is part of my graph. There. And we could draw in the original sine graph and see that this is just a horizontal shift to the left 45 degrees. That's all that's occurred. Now this one. Instead of adding or subtracting something inside the parentheses with the x, we are adding it outside. So a reasonable person would be able to say that that is not a horizontal shift, it's a vertical shift of up 2. Now, if I were to graph again on the scale 90, 180, 270, 360 like this, if I were to dash in the graph of sine, like this, this has what we're going to call an equilibrium. It's an equilibrium right here. It's called an equilibrium because it cuts right through the middle of our graph. Right? We start here, go one below, one above, one below, one above, one below, one above. This is our little equilibrium. Vertical shifts are fairly easy to graph by hand because all you do, we have a shift of up 2. So draw that equilibrium. Instead of being the x-axis, just move it up 2. Draw our equilibrium here. And then you can just graph the sine function as though this equilibrium is now the x-axis. So we're going to go here, one above, back to the equilibrium, one below, back to the equilibrium, one above, back to the equilibrium. So our graph is going to look like that, and it's going to repeat that pattern to the left. So there is our graph of sine of x plus 2. And when I was saying one above equilibrium, one below, one above, one below, that is what we're going to refer to as the amplitude. Amplitude is what we're going to define as how far from the equilibrium do we get. So the amplitude of this function is 1. We get 1 unit away, 1 unit away, 1 unit away, 1 unit away. We don't care if it's above or below because we want to think about amplitude as a distance. And so whether you're above or below, the distance is still positive. So then we have a graph like this. Y equals 2 times the sine of x. Any guesses on how that is going to affect our graph? From our old transformation rules, you multiply outside like this, it's a vertical stretch. So when you have a trig graph where the only thing that has changed is the amplitude, your x-intercepts are going to be exactly the same. So if I'm on the scale, 90, 180, 270, 360, sine hits the x-axis here, 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 and here. But the only thing that changes is instead of coming up to a value of 1, now, because of this, we're going to come up to a value of 2. Instead of going down to a value of -1 here, because of this, we're going to go down to a value of -2. And that pattern just repeats, and so our graph is going to look like this. And that pattern repeats over to the left. So we've got this, where again our equilibrium, since we don't have a vertical shift, is the x-axis. Amplitude is the distance we are from the x-axis, the maximum distance we get, which is 2. And so we're going to define our amplitude as the absolute value of whatever this number happens to be. So we multiplied outside and that changed the amplitude. Now we're multiplying inside. What do we suppose that is going to change? It's going to be a horizontal stretch or compression. Which one? Lots of votes as to whether it's a stretch or compression. Let's let the calculator inform us. So when we threw this in the calculator, we saw that it was a horizontal stretch. And so our new period, we're going to define the period now. You take the original period, since we were working in degrees there. You take the original period of 360 and divide by whatever you were multiplying by in here. So our period is now 720. So let's go with the same scale we've been doing, 90, 180, 270, 360. When we did the horizontal stretch, the sine function usually starts at the origin. Will this start in a different spot? No. If I plug in 0, I get y equals the sine of 0. So we get this same spot here. But our original sine graph is again going to look like this. But instead of taking 360 degrees to repeat, it's going to take 720. So everything gets moved twice as far. So this peak right here is 90 degrees away from the y-axis. Now that peak is going to be 180 degrees away. This 0 is 180 degrees away, so now it's going to be twice as far, 360 degrees away. So everything gets twice as far away from the y-axis. So this is what the right side looks like. Noticing we don't really have enough space on this branch of our x-axis to see a full and complete period. But if we graph everything over to the left properly as well, we will see a full and complete period. And that is from here to here. That is one period of our graph, 720 degrees now. So multiplying by 1/2 inside makes the period twice as long. If you were to multiply by 2 inside, that would make the period half as long.
Why do they do that in math?
We're going to move on to this. This is cosine. Now, the rules that we've learned for the transformations are all exactly the same. It's just now, instead of transforming from the original graph of sine, we're obviously going to transform from the original graph of cosine. And there are 2 transformations occurring. There's a number here, and there's a number here. What are those 2 transformations? Give me one of them. So we have 2 transformations. Our amplitude is now going to be 2, so this was a vertical stretch. And this is a horizontal shift, or the new vocab would be a phase shift, to the right, pi over 2. So we have to be in radians now. So my scale is going to be like this. Now, cosine. The original graph of cosine is going to look like that. My equilibrium for cosine is the x-axis. That equilibrium has not moved because there is not a vertical shift. My amplitude is 2, which means the maximum distance I'm going to get away from this equilibrium is 2. I'm going to get as high as positive 2, as low as negative 2. But cosine, instead of starting here, is going to be shifted to the right pi over 2. So instead of starting at 0, 1, I'm going to start at pi over 2, 2. So I'm going to be here, then here, then here, 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 here. So this part of my graph is going to look, that was terrible, like this. There we go. And that pattern is going to repeat over on this side, which is going to bring up an excellent point in just a minute. There is my graph. So I gave you this function, asked you to graph it. It is cosine shifted to the right pi over 2 with an amplitude of 2. That is the graph. Tomorrow, the type of question you're going to be given is I will provide you with this gold graph, and I will ask you for the equation of the graph. Looking at this gold graph, tomorrow, when I ask you for the equation, I would not at all expect you to give me this. Looking at the gold graph, what is an easier equation to write? If I asked you for the equation for the gold graph, you could say that's just 2 sine of x. It's the same exact thing. Which we talked about last week when we did the graphs of sine and cosine, and we said that sine and cosine were nothing more than horizontal shifts of each other, and we actually did graph this earlier in the notes, and it looks exactly like this. So tomorrow, the questions are going to have to be phrased, write an equation for the graph. Because of situations like this, I can't say write the equation, because there isn't only one choice. There are multiple, and it does not matter which one you write, so long as the equation you write gives the good graph. So here, we have the general form for these equations, sine and cosine. We have an a there, we have a b there, we have an h there, we have a k there. The nice part is those 4 variables, a, b, h, and k, all represent the same exact transformations regardless of if you're dealing with sine or cosine. The only reason sine or cosine are important are obviously the transformations from which original graph. Sine and cosine have different original graphs. But the transformations to worry about, our amplitude is going to be the absolute value of a. So if that a were a -2, our amplitude, the distance, the maximum distance away from our equilibrium, is still going to be 2. It's the absolute value of that number. Then our period is going to be the original period divided by the absolute value of b. So that's 360 over the absolute value of b, or 2 pi over the absolute value of b, depending on whether you're in degrees or radians. It's just the original period divided by that number. Then the h and the k just give us our, well, we'll switch the vocab. We're going to have a phase shift, which just means horizontal shift. That's h. And then our vertical shift is k. So those are the 4 transformations you're going to deal with. The homework has 11 problems in it. 6 of them contain only 1 transformation. The other 5 contain 2 transformations. So that's going to be the homework. So with the amplitude being the absolute value of a, what would something like this look like? How is that going to be different than the original graph of sine? You could use your calculator to figure it out. Sine is going to be like this. That's what sine looks like. 2 sine means from our equilibrium, which is, in this case, the x-axis, we're going to get 2 units away. What the negative means is that here, instead of being 2 away above, we're going to be 2 away below. So the negative is a reflection over the x-axis, which is another one of the transformation rules that we did learn, reflections. And so that is what the graph would look like. So where the original graph peaked, the transformed graph would valley. When the original graph valleyed, the transformed graph would peak.